Hi everybody, this is Mr. Scott. We're going to continue on with worksheet C from the other day that Mr. Murphy started. We're going to pick up with number 2. Okay, we're going to solve this one, factor it, graph it, and do all that good stuff. We're also going to look at what happens when we have two or more of the same roots. That's going to be one of the key parts of today's lesson. So getting to number 2, looking at our possible rational roots, or PRs. Those come from the factors of 18. So we're going to have a whole bunch of possibilities, plus or minus 1, 2, 3, 6, 9, and plus or minus 18. And what we're looking to do here is we're looking to find one root. That's all we need to get this thing started. Now, there are a couple different ways that you can go about speeding up this process. One of which is using the calculator and the table feature in the calculator. Instead of plugging all these numbers in, you could plug this g of x into y1. Okay, and then make sure your table is set to ask. That would be on second window. And then go to your table and just start plugging in the numbers. When I say ask, make sure your independent variable is set to ask. Then just go test on the calculator. So you'd find out by the factor theorem and the remainder theorem that the g of 1 does not work. Okay, you don't get a remainder of 0, so that's not a root. The g of negative 1 doesn't work. I'm just going right in order. That's no. The g of 2 is a no. Does not work. I don't even know what these values are. I'm kind of cheating with knowing what the root is here. But the g of negative 2 is equal to 0. Okay, so by the remainder theorem, we know that negative 2 is a root. Okay, we also know that x plus 2 is a factor. So we're going to list that. So we know x equals negative 2 is a root, which means that x plus 2 is a factor. And like what Mr. Murphy said in the last lesson, we're going to take that x plus 2 and we're going to divide it out of that cubic polynomial. Okay, so we're going to do synthetic division, put negative 2 on the outside, your root. So list my coefficients, making sure every single term is hit from the cubic down to the constant. We're going to perform our synthetic division. Hopefully you guys are experts at that by now. So pull that one down, go ahead with the process. And we should have our 0 at the end. Remember, that's our remainder. So our quadratic here is x squared minus 6x plus 9, which, if you look, is factorable. So we're going to continue to factor. Listen, with quadratics, we're going to look to keep going down as far as we can to see if we can get into linear factors. If this wasn't factorable, I'd leave it in its quadratic form. But this is a perfect square trinomial. It's x minus 3 times x minus 3, or x minus 3 quantity squared. So if we factor this function over the factored form, the g of x is going to be our original factor up here of x plus 2 times x minus 3 squared. Okay, and we say the default is the integers. If we just say factored form, we want every single term in these factors to be integer values, whether it's the coefficient of the variables or whether it's the constant. We could also factor it over the reals, meaning that if this quadratic right here was not factorable, okay, maybe we had to use the quadratic formula to solve and we got real number solutions, we could factor that over the reals using those real number roots as your factors. But in this case, factored over the reals is going to be the same as the integers. Okay, there's no difference there. Okay, now this is where we get into a little bit of a pickle here. Okay, we're going to list all the roots. Well, here I've got x equals negative 2 as a root. Okay, that's our original root that we found by the rational root theorem, or the specialized rational root theorem. Okay, and we also have the root of 3. Okay, that comes from the x minus 3. But if you notice, this is x minus 3 squared. 3 appears as a root twice. We're going to call this a double root. Okay, which is important for a couple different reasons, which we're about to get into. Okay, the first is going to have an effect on the graph. Okay, so I'm going to skip ahead down here to the next page in worksheet C. We're going to do a little investigation. Okay, so what I want you to do here is take a second and graph each one of these functions right here in your calculator. Okay, and what we want to observe is how are these functions behaving around the roots that are embedded in them. So like in y4, how is the graph behaving around the root of x equals 5? Okay, or in like investigation number 4 down here, how's the graph behaving around the root of x equals -2 for that y7 value? Okay, so take a second, graph them. I'll put the graphs on the screen and we'll take a closer look. Okay, so hopefully you graph those and notice a couple things about how they differ. So if you look here at investigation number 3, okay, notice how the graph around that y4, that x minus 5 to the 4th, okay, notice how at the root of x equals 5 that the graph bounces off the x-axis. Some teachers call it like a touch and turn, but it does not cross through. Okay, and this also has to do with like our end behavior of the graph, how the graph is behaving as x goes to infinity or to negative infinity. That'll be covered in a separate lesson coming up in a couple days when we look at graphing these things a little bit more carefully. For right now, we're going to use the calculators for the most part to graph. And same thing with y5. Notice how we have -2, okay, as the root. -2 appears as a root 6 times. Okay, and again, the graph bounces off the x-axis. So our conjecture, even powers, meaning even multiple roots, okay, the graphs bounce off the x-axis. Now, at those roots. Okay, now if you look down here at investigation number 4, you notice how at the root of x equals 5 in this first one, this graph crosses through the x-axis at that point. Okay, and same thing in y7. Okay, -2 appears as a root 5 times in number 7. Okay, it's an odd multiple root. Okay, and the graph also crosses through. Okay, and that's going to hold true for any odd powers or any odd multiple roots. So the conjecture here is the graph crosses through the x-axis at those roots. And again, that's going to give us some important information about how these graphs behave once we go to graph these really without the calculator. So I'm going to move back up here to sketch our graph. Okay, notice how we have a double root. Okay, double root in this x minus 3 squared. Okay, the graph's going to bounce off the x-axis since it's an even multiple root. So bounce off the x-axis at x equals 3. So I'm going to create our coordinate plane. I'm going to list our roots. So I'll go to -2. Make a point. Go to 3. Our double root where we're going to bounce. Mr. Murphy the other day also mentioned the y-intercept is an important point that we need to consider. Our y-intercept here is 18. It's the value of our constant. I'm not going to scale this one, but I'm going to label the point at 18. And again, we're going to use our calculator right now to finish graphing this out. You guys will learn about end behavior, like I said, in a couple days. I note that a cubic, Mr. Murphy also noted the other day that a cubic function that has a positive leading coefficient is going to go up, heading to the right. Notice how we bounce off the x-axis at 3, so I'm not going to cross through it because I got to get back up here to this y-intercept. And then we're going to come down here and we're going to cross through -2 because -2 is an odd multiple root. -2 only appears one time. Don't worry about, for the quick sketch, how high this little maximum point right here is going. We'll learn about that coming up with our calculators. But yeah, listen, with this, it's a matter of bouncing. If I cross through the x-axis at x equals 3, what's going to happen to get back up to this 18? Well, I'd have to kind of come down here. I'll switch colors. I would have to come down here, then somehow come up. And look, right here, we'd be creating another root, which doesn't exist, okay? So these bounces and crosses are super important to consider. Okay, so I'm going to erase this little value, this little thing I created, okay? And there's a general look at our graph, okay? So next big important thing are the multiplicity of roots, okay? So consider whether you have an even multiple root or an odd multiple root, okay? Whether you bounce off the x-axis or whether you cross through it, okay? Number 5, looking down at it, we have a negative leading coefficient. Here's a suggestion. I think it's a pretty handy suggestion. Okay, whenever we have a negative leading coefficient, we factor out the -1 first. Okay, and that's going to help us, factor this thing a little bit easier. Okay, and move forward a little bit more quickly through the problem, or efficiently through the problem. So let's take the t of x. Oh, I'm going to write it down here. I see it there. I'm going to factor out the -1. We have x to the 4th minus 6x to the 3rd plus 2x squared plus 16x minus 32. Or sorry, plus 32. Okay, and we're going to go through the process here. Notice we have a quartic, okay, and this is going to maybe create a little bit more work. Our whole goal is to get this this polynomial down to a quadratic that we can use either the quadratic formula or factoring to solve it. So let's list our possible rational roots, our PRs. Those come from the factors of 32. So a whole bunch here. And we test until we find one that makes the function equal to 0. Okay, we find a root first. Okay, again, this is one where the calculator will help you out. Throw t of x into y1, use your table and test. Okay, and we're going to find out that the t of 4 is equal to 0, which means x equals 4 is a root, which makes x minus 4 a factor. And so that comes down here. We're going to divide that root out of there by synthetic division. I'm going to use my my polynomial where I factored out the -1. It wouldn't matter which one you use. Again, that -1 doesn't have any impact on the roots. So I'm going to use the one where -1's factored out. So we want to keep that factored out at the end anyways. Perform your synthetic division. So 1, sorry. And we get a remainder of 0, which again is what we need. Notice here, we have a cubic, x to the 3rd minus 2x squared minus 6x minus 8 that we're going to look to solve as well. Just a note, when you come down to a cubic, you have a 4-term cubic polynomial, which might be groupable. Okay, if you can group this thing, factor by grouping, do it. Okay, it'll save you a lot of time and a lot of effort. Unfortunately, this one is not groupable. Okay, the ratios of the first 2 coefficients aren't equal to the ratios of the last 2, so you actually have to start the process over. Quartics become kind of a pain in certain cases. So you start again with your PRs, which are going to be the factors of 8. So plus or minus 1, 2, 4, and 8. Okay, again, you can put that in your calculator. Okay, and you notice that again, the t of 4 is another root. It equals 0. So x equals 4 is another root, which is going to make that a double root. And x minus 4 is another factor. And again, we take that and divide it out one more time. So I'm going to take that synthetic root right there. Set up my coefficients from our cubic. Perform our synthetic division. And we get x squared plus 2x plus 2 as our quadratic. And again, once we get down to a quadratic, we don't have to use the rational root theorem anymore. We can look to use our other methods that we learned a long time ago. Okay, so quadratic formula or factoring. Unfortunately, this one's not factorable. But Notice that the factored form, okay, we're going to have our t of x. This is going to be our -1 that we factored out originally. Don't forget about that. Times our two factors of x minus 4. So I have x minus 4 squared, our double root, which is going to have an impact on the graph, times x squared plus 2x plus 2. Okay, that's factored over the integers. Every integer, or every value there is an integer value. Okay, so from here, I want to factor over the reals. Well, notice how we have two other roots that come from this quadratic. This can't be factored, so we have to use the quadratic formula. So let's do that. For AC, that's 4 times 2, which is 8. So I'm going to get -2 plus or minus the square root of -4 over 2, which is going to be -2 plus or minus the square root of -4 is 2 times I over 2. So I got x equals -1 plus or minus I. Okay, now notice here that these are not real number roots. These are two imaginary complex roots. Okay, so factored over the reals is actually going to be, in this case, the same as above. Not anything else we can do with that. Okay, but the good news is that we found all of our roots. So we have x equals 4, which again we're going to list as a double, and -1 plus or minus I. Okay, notice we have 4 different roots there from our quartic, which again is going to be important coming up in a minute. And the sketch of the graph, we'll do this quickly. 4 is a double root. Okay, notice we have to bounce off the x-axis here since it's an even multiple root. Our y-intercept is -32. I had to look up above. And notice here, you might be able to make a conjecture on how this graph is behaving. Okay, well, notice how we can't cross through the x-axis, okay, because of the even multiple root there. So this is going to come down here, bounce off, and then come back down. Okay, I'm not sure how this is behaving as far as like the bends go. Your calculator will show that to you. We will get more into the number of bends and the end behavior again coming up. Okay, but what this all leads into, okay, is this pretty important theorem. It's called the fundamental theorem of algebra. I mean, how do you get any more important than the actual fundamental theorem of algebra? It's fundamental. Okay, that's the most basic concept. Okay, this was developed a long time ago. Which says every polynomial of degree greater than 0 with real coefficients has at least one zero or one root. Okay, and that 0 may be a real number or a non-real complex number. And this was really important back in the day when really algebra was all based on the study of equations, linear equations. This didn't really develop anything into like more modern algebra. But that's for a little history lesson if you want it. It was first proved by Carl Friedrich Gauss, okay, who is my personal favorite mathematician. Every math teacher needs a favorite mathematician. He happens to be mine. But this also leads into an important corollary of this theorem, okay, which says if f of x is a polynomial function of degree n, then it has exactly n zeros or roots, and each zero may be a real number or a non-real complex number, and repeated solutions are counted individually. And this is pretty powerful for us, okay, because what this says is if we know the degree of our function, okay, then we know exactly how many roots we need to produce, okay, if we're looking to solve it. So looking above at our last example, we had a quartic, okay, has a degree of 4. We needed to find 4 roots. And looking quickly above, how many roots did we find by solving it? Well, we had 4. We had x equals 4, which is a double root. Okay, that counts twice. There's 2 roots. Then -1 plus I and -1 minus I were the other 2 roots that had 4 roots. So this gives us some other important information that we need to consider. Okay, so if you're looking at a cubic, think about how many roots you have to find at the end. Okay, and we're going to finish up this lesson with number 6. I'll do A with you, and then you can try B. So it says determine the polynomial function with integer coefficients and with the given degree and roots. So we have a cubic. We'll think, how many roots do we have to have? We need 3 roots. Okay, we're only given 2. We have negative 2/3 and 4i. Okay, so since 4i is a root, we have a missing root of negative 4i. Okay, and we can think imaginary and irrational roots must come in conjugate pairs. And that's really per the quadratic formula, or even in this case, if you were solving by the square root method, if you were missing a linear term in that quadratic, you would need the plus or minus once you square rooted that x squared. So I know that a 4i is a root, the negative 4i is a root. Okay, so we would set x equal to each one of these roots. If x equals negative 2/3 is a root, I'm going to change it into a factor. So I'm going to multiply by negative 3 or 3. So I've got 3x equals negative 2. So I know 3x plus 2 is one of my factors. For the 4i and negative 4i, I'm going to use our shortcut method. So I'm going to use these for the sum. So I got 4i minus 4i, which is 0. Our product is going to be 4i times negative 4i, which is negative 16i squared, which is negative 16 times negative 1, or 16. So our quadratic here is going to be x squared minus our sum times x, so minus 0x, plus our product of 16, which is x squared plus 16. So we have a cubic of, we'll call it f of x, is going to be 3x plus 2 times x squared plus 16. And really the last step here would be to FOIL that thing out, which you would get 3x to the third, not 3x squared, sorry, plus 2x squared plus 48x plus 32. Okay, so there's our cubic that has roots of negative 2/3 and 4i. Okay, so try part B to finish out this lesson. I'll put the answer up in just a second. Pause the video and check back once you're done. So there's the answer to part B. So just to wrap up this lesson, just key things that we covered today. The multiplicity of roots, okay, so even multiple roots versus odd multiple roots, how that's going to impact the graph. Also, how many roots does a function have, whether it's cubic or quartic or even a quintic. You're going to see a little bit more on this topic coming up the next day. I know Mr. Murphy said I'd talk about today how to solve when the leading coefficient is something bigger than 1. That happens to be tomorrow's lesson or the next class's lesson that either Mr. Dooley or Mr. McGivney will cover for you. But listen, with this practice, do your exit slip. Make sure you're trying your assignment. This stuff, yeah, it's a lot of mechanical work, but if you understand the process behind it, it's pretty straightforward. So hopefully this helps. And if you have questions, contact your teacher. Thanks. Take care.